Well, howdy. All right, so I want to do the third part of this lecture. I've got about 7 parts, I think, of potentials and fields. We're talking about potentials, fields, work and energy, and all that other fun stuff. We're not just limiting it to fields here. But right now I'm still doing fields. I just finished one question, a qualitative question with some capacitor plates. Now I want to go into something that's a little more quantitative, sort of semi-quantitative. I'll do some quantitative things. But we want to look at some potential, some data about potentials and turn that into electric fields and then compare those fields. So here I've plotted some data on what the potential is at different points in space. So I'm just going to, in a single direct line, figuring out what things are going on in space, right? I'm assuming that perpendicular to this line, everything is exactly the same, that there's no change in the potential, that everything in a straight line across your screen has the same potential. So this is a really interesting thing. You want to be able to look at something like this and figure out what the largest and the smallest magnitude of an electric field is right away. You want to be able to do that, especially by the time the tests and the finals come around. So why don't you take a peek at this and tell me what you think, right? Pause, think about it a little bit, write down why you think what is what, and so forth and so on. And then, I'll go ahead and work the thing. So just pause, think, write. Writing is important. It's very important to actually write down what you're thinking, all right? That means a world of difference. Okay, that's about enough. If you didn't pause manually, then it's too late now. So how did I look at this, right? And that's a good question. So, well, what I did was I used this nice little equation here that we've been talking about already, and I just rewrote it a little bit, right? I said, okay, E is equal to minus delta V over X. So yeah, rewrite it, and this will let me find the electric field at each one of these points, and we can just do this completely quantitatively. So I'm going to make the prediction now that where this is steepest, this 1 is where you've got the largest magnitude, and where it's flat here is where it's going to have the smallest magnitude, okay? This may be a negative number here for the field, but, well, actually this is going to be the negative number for the field. This might have the opposite direction, but the magnitude in one dimension is just the absolute value, all right? So let's go ahead and see what we have to do with this. Well, what am I going to do? Well, I've got 6 different things. So the first thing I'm going to do is I'm going to make a list. I'm going to make a table of all of these 6 different things, and I'm going to go through and do whatever I need to do with those 6 things. And I'm going to do this by reading the graph, right? So here I've got plus 6 volts from where I start to where I end, and here I have 1 centimeter difference. So when I put those in my table, I go off and I try the next one. Minus 2 volts versus 2 centimeters. Minus 2 volts versus 1 centimeter. Plus 4 volts, we raise up 4 volts in 3 centimeters, which is probably the longest interval there. Then no change over 2 centimeters, and 1 volt up in 1 centimeter. All right, so that gives us all of these things that we need. Now now that I've got all that data, I'm just going to divide the two numbers and put in a minus sign. So for this first one, it's 6 volts over 1 centimeter. That's 6 volts per centimeter, which is what? 600 volts per meter. And it's a minus sign because the delta V is a positive number, and there's a minus sign in the equation, right? So that's minus 600 volts per meter. And 1 volt per meter is equal to 1 Newton per Coulomb. They're the same unit. They're exactly the same unit. And you can spend as much time as you want trying to prove that, and you'll prove it, and it'll be wonderful, right? I'm not going to go through and prove it. They're the same number. They're the same number. One of these is one of the other. All right, pretty nice. So what's this next one? It's minus 2 volts over 2 centimeters. That sounds like 100 volts per meter. Minus 2 volts over 1 centimeter. It's minus 2, or that's plus 200, excuse me. 4 over 3, that's minus 133, I think. volts per meter. 0 over 2, that's flat. There's no electric field there. That's what no electric field looks like. You can have a positive potential, but as long as it's flat, you have no field. That means there's no force on something either, right? The field is proportional to the force on a charged object. When the potential is flat, there's no field. That means that whenever the potential is flat, there's no force on any charged objects. There's no electrostatic force in this region 5. No force in region 5. And then for 6, you end up with minus 100. Simple, easy, the exact sort of thing that you like in a physics class, right? So if that makes sense, you can go on to the next thing. If not, go through it again and again and again. Go through it till you're happy. It'll be something that benefits you later, all right? So thank you very much, and I'll talk to you in just a moment.